Okay, so we have started, we finished the acid and base, and with that we have already discussed about the solubility, pH of the solution, and how the titration would look like, what type of indicator should we be using for our titration, and all those things. One thing was left here, that is the buffer solution. That we already have seen the buffer solution last lab, and I am assuming that you already have your hands-on training on it. So you have some practical experience. Now you're going for the theoretical one. So you can have much input into it, and also can have some good reference or discussion on it. Yeah. Okay. So what is, and the solubility of the product. Later we'll see what is the, so our aim to do this today. Okay. So our aim to learn this unit today is to describe the common ion effect. What is the common ion effect? The name implies that the ion should be common in between them. One ion should be common in between them, among them. And also, this common ion is one of the main cause that is creating the buffer solution. So we will know how this common ion is creating the buffer solution as well, and how the buffer works, and how to prepare a buffer with our desired pH. That we want that buffer to be within this pH. How to create that, what should we do? And the solubility equilibria for one type of sport or a compound that will be dissolved in the solution, but we want to know the, what is the maximum capacity for that ion, that chemical to be dissolved. To what extent will it be dissolved in that? So the ion constant, solubility constant, we will be looking at it. Common ion effect, according to the Law-Shortlist principle, it says that when one system is in equilibrium, right? Law-Shortlist, once again, we talked yesterday. So it says that when one system is in equilibrium, then if we add or change the we add something or change the environment for that equilibrium, the solution or the reaction will move towards where it can sit or it can have a good equilibrium again. So same thing. How do we change? What are the medium that we can change one equilibrium of a chemical reaction that had attained the equilibrium? What are the factors that we can change to disturb the equilibrium? I think I talked yesterday. So anybody from online as well can say what are the factors that we can change to disturb the equilibrium for one reaction that has attained the equilibrium. They are quite few, right? So what are those? Pressure, temperature, concentration, and heat as well. Right? So here for the system that is working, let's say, in a very small area or not exposed area, so we cannot add pressure or add temperature to that. So what we can do is we can change the concentration. Right? So common ion is one of them that is going to create that type of discrepancies or disturbance for a system. So for a common ion, it's called that for acetic acid or ethanoic acid, We see. How does it change the acetic acid? We all know that acetic acid will be dissociated in a way that it produces acetate ion and hydrogen ion. Right? And this is a both way reaction, so it equals, I mean, it what do you call it, attains an equilibrium here. So these things are the product. If we add more of this or more of this, the reaction should go behind, right? How do we add? How can we add? If I keep adding acetic acid, will that, it will increase this CH3OOH and hydrogen plus. But does it mean that I am increasing these two? It doesn't. Because the more you add acetic acid, it will go here, according to Le-Chatelier's principle. The more you increase here, it will go towards here. But I have to increase here so that it goes this way. How do I increase this side? I have to add some kind of salt which has this so that it will be dissociated and it will put pressure on the system, right? And sodium acetate, you see these two are the same. These two are the same. So that is why we call this a common ion. In these both chemical compounds, these two are the common ion. Can you see, are you talking, asking anything? No, just hi, hello. Okay, so these two are the common ions. So what is the effect for them? What will be, how will it affect the system? It will push which one? It will push this way or it will push that way? Which one? Which reaction will be pushed behind? One or two? One. Why? One? Sorry? I didn't get. Yeah, it's a quiz question. Let's say it's a quiz question. Why one will be pushed, not two? Why one will be pushed, not two? I know you know, but you're not thinking that way. Anybody knows why in between these two common ions, if we are adding, right, these two are the same ions. So if both are in the system, one reaction will be pushed behind, according to Le-Chatelier's principle. Go behind. One, reaction one or reaction two. One, our friend says that reaction one will be pushed behind. Backward, sorry. So my question is, why reaction one? Why not reaction two? This is the correct answer is reaction one, okay, but why? Why? What is this? And this? Acid, weak acid, and salt. Salt is always dissolved, always dissociated. 100%, it will always get dissociated. Salt are electrolyte, so they will get dissociated no matter what. So that means if you put more, it does not care, and moreover, it is a one-way reaction. So you know, from the reaction is one way, there is no way back for it. But for it, yes, there is a back because it's a weak acid. Okay, so this is common ion between them, and the reaction is going backward. So the reaction shifts to the pH of the solution. If it shifts backward, it is taking this hydrogen ion along with it, right? it is, I mean, going backward means hydrogen ion is also reducing in the system, right? Otherwise, where this hydrogen ion is coming from? I am giving this, and I am getting that one when the reaction going backward. So this hydrogen ion is also getting reduced from the system, right? And since hydrogen ion is getting reduced, the pH of the solution will increase. The pH will go more than neutral. I mean, if it were 5, it will go to 6, maybe it will go to 7, right? Okay, so this is one thing that that is how we can reduce the acidity of the solution. Okay. Now, we saw it for acid. What about for base? What about for base? Does it same thing happen for base as well? Yes, it does. For base, it is also occurring the same way. Once, when it is a weak base, it will be dissociated partially, and then because of its partial dissociation, we can push it backward as well. All right. So for the ammonia, weak base is ammonia, and ammonia has been produced for ammonium chloride. Ammonium chloride is a salt, or ammonium phosphate, ammonium nitrate, whatever you say, is a salt. It will be dissociated, all right? But if it was ammonium hydroxide, it is ammonium hydroxide, what will happen is, ammonium hydroxide is a weak base, right? Ammonium hydroxide is a weak base, so it will dissociate partially and it will give ammonia and hydrogen, right? Will it give ammonia and hydrogen? No. Will it get ammonia and hydrogen? Anybody from online? I checked the video, it is not that clear, and any better idea what can I do? Okay, on the solution, the base is weak, right? So, such as ammonia, it will, and a salt of the base, sodium ammonium chloride. So, ammonium chloride, when it is in the system, it is producing ammonia, ammonium, and chloride. One step is not shown here. So, ammonium chloride, it is giving ammonium and chloride. This ammonium is here, it is shown, right? So this ammonium, after it becomes ammonium chloride, where is ammonium chloride here? Oh, yeah. This ammonium chloride goes to the water, because it is a salt, it will dissociate fully. But after it being dissociated, this ammonium is going for, because ammonium is a weak acid, right? Ammonium is a weak acid. It is going for this hydrogen ion and ammonia. So this ammonia is a base again, right? So if we take the Ka, because this is an acid, if we take the Ka, acid dissociation constant of that ammonium ion, we get this. I mean, this is the equation. Of course, we know all this. I mean, already. So from here, if we want to know the pH of the solution, from here, if we want to know the pH of the solution, just rearrange it a bit so that we get the hydrogen ion from here, and we can get the pH of the solution. Once the ammonium chloride or the neutral or ammonium chloride should be, what type of salt will it be? Ammonium chloride. Ammonium chloride, what type of salt is it? Acidic, basic, or neutral? ammonium chloride. What type of salt? When it gets dissolved in the water. Is it an acidic solution it produces, or basic solution it produces, or neutral? Which one? Sodium chloride, it produces neutral, right? You know. Potassium chloride, it produces neutral. Ammonium chloride, whether it produces acidic, basic, or neutral. There is one chat, I think. Basic, okay. Mildly acidic, sorry, okay. I think it is acidic, yeah. So there are some online students, they are commenting that it is acidic. Yes, because ammonium chloride is dissociated, ammonium and chloride ion. This chloride is not going to do anything because chloride does not interact further. This ammonium is going for hydrolysis again, this producing hydrogen ion. So this solution is producing a little bit acidic, and that is why it is acidic. Okay. So it occurs also with basic salt. Can occur in this category, right? In this category, for reaction number one. For reaction number one, let's say, I am adding some more ammonia into the solution. I'm adding some more ammonia into the solution. What will happen? The reaction will go backward, right? The reaction will go backward and ammonium produce. This ammonium will produce maybe with other anion is there, it will be added. So probably it will be ammonium chloride, ammonium, what is that, ammonium hydroxide, okay, or whatever. So if we put more ammonia into the solution, it will produce a backward, and then thus it will be, ammonia will be the common ion here that we can produce. So this common ion thing not only occurs with acid, it can also occur in a basic medium. Example 1, it says the calculate the pH of 0.2 molar acetic acid solution. And here it is interesting that we are not going to do the number A, example 1A, because this type of problem we have already solved many times, right? Have we solved this type of problem? No? Very familiar or not? Familiar, right? Initial, then acetic acid is a weak acid. It's already done actually, I don't need to do. It's a weak acid, so it will be dissociated partially, and that is why it will have a both way arrow, both way direction. And since it is 0.2 molar, 2 molar, and we do not know how much of this acid is going to be dissociated, so we consider it X, right? It's very similar, very familiar to us. So this is very familiar to us. 0.2 molar at the initial stage, we did not know. Take note here, yeah? Those are online, take note. Okay, so, oh, I can see here at top. Yeah, yes, here, yeah. Okay, so here, take note here that at the initial stage we had 2 molar, and then at initial stage the hydrogen ion and acetate ion was 0, right? Acetate ion was 0, both cases. Okay. So these two, these two cases, it is 0. Sorry, remember these two part, that it is 0 at the initial stage. And then of course Ix amount, that is a very small amount, changes at some point. So we deducted it from the equilibrium and get this Ka value. Ka value was given 1 times 8 10 power 10 negative fifth. So we got this. And from there we find the hydrogen ion concentration. So we assume that is the approximation method, and we find the pH of the solution. The second thing is the second question. Question B, right? Question B says that in a soluble that, what was that? Question B was, what is the pH of a solution containing both acetic acid and sodium acetate, right? Sodium acetate and acetic both, and they could be same strength, but in this case it's a different strength. They could be same strength, doesn't matter. So these are two different strengths, and they were there in the solution. So the Ka is given for the acetic acid as well. Now, what is the pH of the solution for number B? pH of the solution. So what will happen is, acetic acid is getting dissociated, but sodium acetate, sodium ethanoate or sodium acetate, something, it is getting more dissociated, because fully dissociated, because this is a salt, right? This is a salt, so it is getting fully dissociated. Now, this 0.3 molar is overpowering this 0.2 molar of acetic acid. This is the interesting here. Okay, so this is 0.3 molar acetic acid, and the next line we have done it is this one. So that's why I was saying that remember this part. Note this part. Initially we have 0.2 molar of acetic acid, and then at the initial moment, at that moment, we already have 0.3 molar of acetate ion, but not hydrogen ion, because sodium acetate dissociated gave us all three, acetate ion and sodium ion. Doesn't matter with the hydrogen, because it doesn't have hydrogen. But acetic acid then at the same moment, it gave me 0.2 molar sodium hydrogen ion, acetic acid, but it does not, all of it does not get dissociated. Only X amount get dissociated, right? So this X amount getting dissociated, and this X amount is on top of this 0.3, it is getting added up, right? Okay. Okay, so this is on top of this 0.2, this X amount is that has been dissociated is getting added up. So this part, please take note, 0.3, can I take control from here? 0.3 plus X, 0.3 plus X. I cannot ask for control. Okay. So now, again, only this part is the difficult thing. Later on, everything is simple. You do the same way. Ka is equal to that acid dissociation, ions over the main acid, and from there we will do the approximation method, and so everything is easy. Okay, we do the approximation method, and we get this value for K or X, or that is hydrogen ion, But if it is not within the validity less than 5%, so we have to go for this quadratic equation later on, right? So that is the only thing. Okay, there is this type, sodium acetate and acetic acid. Just now we talked, right? So there were common ion between them. Acetic acid, CH3COOH. This is giving us acetic acid and hydrogen ion, and sodium acetate, it is giving the same thing, CH3COO. So this is a common ion between these two chemicals, and they are giving us, if this type of common ion are present in a solution, given that they're the weak acid or weak base between them, so Henderson-Hasselbalch equation can be used to find out the pH of the solution very fast without going all this ICE table and blah blah thing. We can just put the value in and find out what is the concentration or pH of the solution. Henderson-Hasselbalch equation. So Henderson-Hasselbalch, how does it come? Let's say sodium and anion. So there's A can be anything, acetate, formate, whatever it can be. It is a weak, it's a salt anyway. It's a salt. So this salt, and there is an acid of the same anion. So both of them are in the solution, and now Ka of the salt, Ka of the acid dissociation constant, we find from there, from this equation. So from here, if we want to know the pH of the solution, right? pH of the solution from this equation, we have the hydrogen ion, so you want to take the hydrogen ion, rearrange it to get the pH of the solution. We just rearrange it, and then we just take the negative log on the both sides so that we can have a nice equation of getting pH. And naturally, when we take negative log Ka is coming here, and this is making us pKa. Negative log Ka is the pKa, just like negative log hydrogen ion is the pH. So negative log Ka is the pKa value, and then hydrogen ion. Hydrogen ion, it was negative here. So hydrogen, acid was numerator, and anion of that acid was denominator. When it was negative, it was changed to positive. So these two identities switched. Numerator goes denominator, denominator goes to numerator. So this is the thing. And this is the Henderson-Hasselbalch equation. So this is very interesting and very useful equation actually, Henderson-Hasselbalch. pH equal to pKa plus log and the ratio of anion over acid. If we want to know the pH, and if we know all those things, just plug in the value or get the pH. Or if we want to know what will be the pH of the solution, or what is the buffer, what is the ratio of the buffer will be, we just need the logarithmic ratio of that acid and anion of that acid, so that we can find a buffer. We will do that later on. So now this is the example. This is the example for Henderson-Hasselbalch equation. Usage of Henderson-Hasselbalch equation. Formic acid, 0.3 molar formic acid we have, and then 0.52 molar of potassium formate. So this is the salt, right? This is the salt, this is the formic acid. Have you ever seen a failed formic acid ever in your life? No. Never get bitten by the bees, or the red ants. So the bees, the red ants, they have their formic acid in their, they impregnate us, and that's why it's burning. We get burning sensation. So this is the same acid. And what is the pH of the solution containing 0.3 molar of formic acid and 0.52 molar of potassium formate if pKa of the formic acid is given, right? So in this way, we can just use the Anderson-Hasselbalch equation, pH equal to pKa plus logarithmic of these two, the ratio of these two, right? So easy, you can, in one line we can finish it. Again, one line we can finish it. So pKa value is for the formic acid is given. Of course, Ka should only be for acid. It cannot be for this. Ka can be only for acid, isn't it? Ka means acid dissociation constant. So of course it can be only for acid, it cannot be for base. So pKa, whatever it is for the acid. So this is given, this value is given, they are asking what is the constant, pH of the solution. This is only the thing, the information is given. So we will find this one. We will try to plug in these two values, A, negative concentration, and HA, concentration. A, negative concentration we can find easily because this salt is much higher concentration than acid, right? So this is the negative A. It will all dissociate 100% and we get the A from here, right? So formic acid format, since it is higher concentration, 100% of it will be dissociated because this is salt. It will dissociate. So 100% or 0.53 molar of acetate ion will be produced. Here we can plug in, but acid, 0.3 molar acid. Again, what we do is a weak acid, it does not get dissociate that much, only small amount. So it was supposed to be 0.3 minus X. We just consider approximation method, 0.3 is minus X is 0.3, right? So yeah, here it is. So we get the 4.01 pH of the solution. Buffer solution. Those online can hear me clearly. Do you follow? Okay. All right. Okay, good. All right. Okay, so a buffer solution. What is a buffer solution? What do we understand about the buffer? Did we try the buffer solution last lab? We tried the buffer last lab, right? What was it? The buffer solution. Okay, it's given a weak acid and a weak base. Or weak acid, it has to be weak. Both acid and base can produce a buffer, but it must be weak acid or weak base, right? And then it must be, there is a salt of that weak acid or weak base from the anion of that weak acid or weak base, all right? So the salt must be from, there should be a common ion. There's in one sentence, there should be a common ion of that weak acid or weak base in that solution, and then the buffer. So the buffer, it can resist the changes of pH, we know. Action of buffer solution, so sodium acetate and acetic acid, they are producing a buffer solution because they can resist the changes due to their common ion, and we see that, yeah. So we add a strong acid. This is sometimes it is confusing. It is very easy. It's a very easy concept, but if we do not practice, it is very confusing. Okay. So one thing, if I add strong acid, of course you cannot add 5 liters of acid and expect the pH does not change, of course, right? You add 2 or 3 drops of strong acid, still the pH does not change. So that is the buffer solution. How the mechanism? This is the mechanism. If we ask you what is the mechanism of the buffer solution, you need to do this one. Okay. So strong acid, if we add, what is happening here? This is the acetate ion that is being here. It is being forced. What is that? Yeah, this is here. It is being forced to produce more acid solution. So acid, adding acid is getting more acid, right? Sometimes it is confusing. I say like, okay, show the mechanism, students show the acid, and then it is producing base. No, it doesn't. Acid, when we are adding acid, it is producing more acid solution. The system is being forced gas way, right? And then when you are adding base, it is going to produce more acetate ion and hydroxide ion. So everything, both acid and base, right? Both acid and base, we are adding only this reaction, this acid dissociation reaction is being affected. This salt dissociation that is happening here, this equation is not affected by for the buffer action. It is only a supporting thing for producing the buffer. You see, we add hydrogen, that means from acid, it is getting the acid from here because we are adding hydrogen. More hydrogen means the reaction is going backward. I add more base. I add more base here. Where is that? Oh, yeah, I add more base. The acid reaction is going forward. So everything is happening for the acid dissociation, not with the salt. Right? So this is the thing that you need to remember. This is important. So therefore, the pH will be resistant to change. Example of buffer solutions. There are buffer solutions. Of course, we need the intravenous solution for life-saving thing, right? For drugs and for medicine, all those things. This is the intravenous solution that we need. If you have dysentery or you're dehydrated, you go to anything. You fainted, lightheaded, anything, go to the hospital, the doctor will give you this intravenous solution. First of all, they want to make sure that you're hydrated, your body is functioning well, your blood is flowing. So this is the buffer solution. All right, this all the solution, the saline actually, this is the buffer. Because directly, when the solution is going directly to the blood, it must be made sure that it is not anything that is reducing the pH of our body. And this is maintained by this bicarbonate buffer. And this is so important, this carbonate buffer, that the whole world or Earth, the system, actually ecosystem is working just because of this buffer. Carbonate buffer. The whole Earth, there are all the lives on this Earth is dependent on this buffer or because of this buffer action, bicarbonate buffer action. Probably if you take the environmental technology, you will know more about it, environmental engineering, in fact. you know more about this bicarbonate buffer. But this is one of the most important that our ecosystem is working in the world. I'll just finish after this. So there are few pairs. It says that whether there will be buffer or not. First is potassium hydrogen phosphate, right? And phosphoric acid. Potassium hydrogen phosphate, sodium chlorate, and perchloric acid. This B, A is potassium dihydrogen phosphate, B is sodium chlorate and hydrogen perchloric acid, and C is pyridine. This is called pyridine and pyridine hydrogen chloride. All right. So there are three possible arrangement or pairs. Which of them will be buffer and which of them will not? All right. So number one, it says that solution three, number one is that is there enough weak acid and weak base? Weak acid, sorry, if there is weak acid or weak base. For phosphoric acid is a weak acid, right? Phosphoric acid is a weak acid because it does not give hydrogen ion that easily. One hydrogen ion is enough for it, and too hard to get from it. So this is a phosphoric acid and it's a weak acid and it dissociates partially, so it produces equilibrium, right? And then potassium hydrogen phosphate is a salt that is coming from this anion. That salt is produced from that anion of the phosphoric acid, right? So buffer solution, this is a salt and this is the acid. So this salt should be produced from that anion of the acid. This is the main thing of a buffer, that it must be weak, whether it is acid or base, and also it should have something, the anion, that is coming from that acid or that base. Right? So yeah, this is it fill up the conditions. So yes, it is a buffer. Number two, B. B, is that a weak acid or weak base? Perchloric acid is strong acid, very strong acid. So first, in the first category, it cannot pass. So it failed. It is not a buffer. It cannot be. You don't need to say anything else. Third is, this is a pyridine, yeah? Pyridine, C5H5, C5H5 aniline, yeah? It's not pyridine, probably aniline. So is it a weak base? Yes, it is a weak base, and since it is a weak base, it dissociates partially, so that it is a conjugate acid of that weak base, and the common acid it has is aniline hydrogen chloride. So this is the common acid. It's the same thing, right? So both in buffer solution, both of the chemical compounds should have the same species in between them, and that is why they are buffer. Since they fulfill all the conditions for the buffer, they are buffer. Yes. So this is a buffer solution. Okay, so I think the time is up for today. Oh, 1 minute over. So I'll see you tomorrow. Not tomorrow, sorry. Next Monday. Next week is the mid-sem, yeah? Mid-sem. Next week. Tuition week. Yeah, so there will be no class for tuition week, but I'm available if you want to have any discussion about your assignment or anything. So should be okay. I'm available. Let me know, please. So all the best. I'll see you after the tuition week then. Oh, for this week, there will be a quiz, right? There is a quiz number 3 for this week, if I'm not mistaken. Anyway, I will announce it on Canvas if there is a quiz. Okay, all the best. Okay, take care. Bye-bye. You may leave. If you have any class now, you may leave. You don't need to wait.